All right, good morning, everybody. This is Math 0310. It's April the 12th. A couple of announcements to start the day. WebAssign is due on April the 15th. I think you have one section due on April the 15th. Office hours, I kind of laid it out day by day here, starting today from 11 to noon, and then on Sunday evening from 8:30 to 9:30, Tuesday from 11 to noon, and then next Wednesday and Thursday, remember, I will be on campus for those hours from 4 to 6 on Wednesday and 9:30 to 11:30 on Thursday. So be thinking about if you want to come by and see me in person and go over some things. That'd be great. I'd love for you to do that. Also remember that other times can be made sometimes by appointment. So other times by appointment, you just got to email me or remind message me, and we'll try to set up some kind of a time. So I'll be happy to do that, and I've definitely done that with people through the semester, so I don't have a problem with trying to do that. The Exam 3 review, I posted earlier in the week on Monday, so you've had a couple of days with it already. Please start working on that review. Doing WebAssign homework is not enough to prepare you for the test. You've got to work on that review. In fact, the best way to prepare for the exam is to go through the review. And also, the more problems you can work on the review without anything in front of you, the better off you're going to be. Because you're practicing what a test is like when you do that. So please be working on the review. All the solutions to the review, obviously, are going to be up there as well. So the window for Exam 3 opens on the 19th. Remember that you can use a scientific calculator on the test. And it seemed like at Exam 2 we had some issues with people getting to a testing center and everything, and all sorts of different little issues going on. So let me emphasize that this is your responsibility to get yourself to a testing center with the appropriate amount of time to be able to take the test. You know, I would get to it. They're not going to give you the test if you get there less than an hour to closing time at the testing center you're using. That's just their policy, which I understand that policy completely. So please take that responsibility on and get yourself to where you need to be at the right time. I would allow at least 2 hours, 2.5 hours to take the test. Not that it should take you that long, but the more time you leave yourself, the better, I think. Finally, a little bit about today. So today we were going to continue talking about functions. We introduced the idea of a function last time, and we've been dealing with functions now. Last time we did, or today we're going to work with function notation. And then we're going to look at talking about domains and ranges from graphs. And then finally finish by talking about graphing functions, different kinds of functions by plotting points. So some basic things about functions that a college algebra student would need to know when they walk into college algebra. And if you can do these things when you walk into a college algebra class, whether it's in the summer or in the fall, man, you will be in so much better shape than most of the class. And so you will be in a strong position to start off a college algebra class. So I just wanted to kind of remind you of that. All right, so our first goal here is to talk about function notation. Oh yeah, before I do that, and one other thing, next week, just remember that with next week, Tuesday we have lecture, right? Just the same as always. We've got a little bit more material to finish for the semester. That material will not be on your exam, by the way. It'll be on your final exam, but not on Exam 3. So Tuesday we have lecture, and Thursday, obviously, no lecture because I will be on campus and we will have started the Exam 3 window. So I just wanted to make sure you knew that. And then the following week, Tuesday we won't have lecture, and Thursday we will. And we're actually really close to finishing up when we do that. After today's lecture, after I post this lecture, 3 more lectures for the semester, and we will be finished. So it'll rapidly be coming to a close. All right, so function notation is our first goal here, to talk about function notation. And so I want to, don't forget that with functions, that every domain must be assigned to something, or you've got two restrictions on a relation. Every domain must get assigned to a range, right? That's one condition. So that the word every is the important thing there. And then the next part is that every domain is assigned to exactly one range. Right? And so the important words there are exactly one. So those are the two restrictions for something to be a function. Every domain has to be assigned to something. And then the second restriction, every domain must be assigned to exactly one range. All right. So we have this this particular set of ordered pairs right here. And this set of ordered pairs satisfies the definition for a function. Remember, also with functions, another thing that we wrote down that makes it easy sometimes to look at is that repeated y values are okay, or repeated ranges. And repeated x's are not okay, right? You cannot have repeated x values because that means you have one domain that's assigned to more than one range. All right, so repeated y's are okay, repeated x's are not okay. So in this little set of ordered pairs here, no repeated x's at all. So this is definitely, this little relationship here does satisfy the definition for a function. We might name it f. And so some notation here. First of all, and we've talked about some of this already, but just wanted to write this down again. So the domain for f is the set of x values, right? So we talk about the domain of f with a capital D with a subscript of f, and that's the notation for the domain of f. And the domain of f in this problem would be 1, 2, 5, 7, and 10. And then the range of f would be the set of y values. So in this case, 2, 3, 8, 9, and 11. Like that. And then function notation. Don't forget what function notation means in this context. Function notation means that if you use, and you write down the symbol f of 1, remember you read this f of 1. And it doesn't mean multiplication or anything like that. This is what we call function notation. And this is saying, what does the function f assign the domain value 1 to? Right? And so f of 1 in our particular function would be 2. And then we could write the rest of them out also. F of 2 would be 3. F of 5 would be 8. F of 7 would be 9. And f of 10 finally would be 11. Function notation is a nice way to write out how a function assigns domain values to range values. A set of ordered pairs is one way that you'll see a function written out, but there are other ways that a function will be written out besides just a set of ordered pairs. Another way might be a table, and so let's make the table actually mean something in this case, not just some numbers. So let's say we have this function that takes the number of hours that you study for your test, number of hours studied for exam, and let's say that that's one row of values here. And then that relates that quantity to the grade on the exam. All right, so let's say that and it depends on the problem, the situation, whether this might be a function or not. It's possible it's not a function, but I'll set it up so that it is. So let's say we have a person that studies 3 hours and makes a 72 on an exam. Another person studies 4 hours, makes an 80. Another person studies 2 hours and makes a 61. Another person studies 10 hours and makes a 90. And another person studies 12 hours and makes a 93. Right? And so in this particular relationship, if that was just your little table of values there, so sometimes you'll see a function expressed in table form like this. And in this particular function, let's call this function something. We'll call it g. And so what could we write here? It is a function, right? Every domain is assigned to something. Every domain is assigned to exactly one thing. So when I write g of 3 here, that means this function g takes the hours 3 and assigns it to 72. Right? The person who studied 3 hours made a 72 on the exam. The person who studied 4 hours made an 80. The person who studied 2 hours made a 61. The person who studied 10 hours made a 90. And then finally, the person who studied 12 hours made a 93. Right? And so that would be the way you'd write function notation in. So a table like this is a way that you'll see a function expressed sometimes. Right? So you'll see a set of ordered pairs like I have here. You'll see a table like I've got right here. You'll see other ways that functions will be expressed. Another way that you'll see a function expressed is with a arrow diagram. So with an arrow diagram, a lot of times what you'll have is the domain kind of in a big circle and the range in a big circle also. So let's say that you've got the domain is a set of people. And I tell you what, let's use the people that I've got with me online right now. So these, Gianna, you only have 2 N's in your name, not 3. So Gianna and Raina and Sandra and Taylor. And I will go ahead and put my name in here too, just so we'll have another one. So that would be the domain right there. And we'll say that this is our favorite color function. Right, so you've got red, green, yellow, blue, purple, pink. What other color? Did you say, Sandra, did you say brown? Okay. Brown, black. What other color should I put in there? Is there another color that I'm leaving out?
Orange.
Orange. Anything else? All right, so that's our range. All right, so let's see. So in an arrow diagram, what you have is Sandra already told me that brown is her favorite color. So we draw an arrow from Sandra to brown. And so Gianna, do you have a favorite color?
Blue.
Blue, all right. And by the way, just because somebody's taken a color, so blue and brown, don't think that you can't choose that color also. All right, so Raina? Do you have
Red.
Did you say red?
Yes.
And Taylor?
Blue.
All right, good. And, to be honest with you, I don't really have a favorite color. This kind of comes up all the time, and I just don't care. And so I don't know if that's a guy thing or what, but to me, it just doesn't matter. And so I will say just to do something here, I'll say that orange is my favorite color, though it doesn't really matter to me. So first of all, notice that this is a function because every domain does get taken to exactly one range. Notice in an arrow diagram what can't happen. So this can happen, first of all. Remember, this is the domain, this is the range. So this can happen. This is okay for two domains to have the same range. So that's okay in an arrow diagram. This is not okay, though, where you have in the domain one domain and then two arrows coming off of that in two ranges. This is not okay, right, when you have a function like that. So with an arrow diagram, our arrow diagram was just fine. So this does satisfy the definition for a function, and you could use function notation here. So let's say, this is our color function right here, so we might refer to this as C, and so you have, I'm not going to write them all down, but you'd have C of Gianna is equal to blue, right? There would be nothing wrong with writing it that way. C of Raina would be red, right? The domain value goes inside the parentheses, and you're saying that this color function C is taking the domain element, in this case either Gianna or Raina, is taking that domain element to the range element that it's being assigned to. Okay, so let's see, favorite color function, so you could do all sorts of things with color. So another thing would be like everybody gets assigned the color of their eyes, right? That would be another possibility. Or everybody gets assigned to the color of the socks that they're wearing or the last pair of socks that they ever wore in their life. So like, for example, right now, I've got black socks on. So I would be, that would be what I'd be assigned to. So all sorts of different things you could do with color that you could use for functions like this. So what's the color of the last car that you drove would be a good example of a different kind of color function that you could have that's assigned to you. What's the color of your hair, right? That would be if you had hair, right? Like, unfortunately, maybe I don't have so much. So, so all sorts of different kinds of functions like that you could use for color. And an arrow diagram is a nice way to show a color function like this. All right, and then another way that let's see, did I write it? Yeah, so arrow diagram. And then the next way we talk about a function is with a graph, right? And with a graph, you might see this a couple of different ways. First of all, there are functions that just use a bunch of dots, and that's the graph, right? A function that's defined discretely, maybe something like this, right? And this graph that I have right here would represent a function, right? And now when you're talking about a graph, notice you can use the vertical line test, which is something we talked about in lecture last time. But this graph passes, let's see, so the graph passes the vertical line test, right? No vertical line intersects the graph more than once. So this is a function. And then, you could name the function, like we could name this function h, for example, right? And then you could write down the domain of h, right? The domain of h is just the set of x values that you're using. So in this problem, the set of x values that I'm using, let's see, it would be -2, -1, 2, 3, 5, and 7, right? Those would be the domain values for this function h. And what did I do there to get those values? I simply looked at each ordered pair and figured out what x-coordinate went with that ordered pair. So I looked at each dot and I figured out what the x-coordinate for that dot was, right? So this first one, this is -2 something. The second one, this is -1 something. This one right here is 2 something. This one is 3 something. This one is 5 something. And then finally, this one is 7 something, right? So I just looked at each dot on the graph, and I figured out what its x value was. And then the range, I'll put that in a different color, the range on h is simply the set of y values that you're talking about. And remember, these could be repeated. These are okay to repeat. So the y values are positive 1 for that first point, positive 3 for the second point, 4 for the third point, positive 1 for that one, negative 2, and then 0. And so that would be the range in this case, just the set of y values. 1, 3, 4. We don't need to write 1 down again. Negative 2 and 0. You can write them in numerical order if you want. In an increasing value, you don't necessarily have to do that. And actually, though, the more I think about it, I would want you to do that. The more I think about it, because that's what we're going to do with other kinds of graphs also. So I'm going to erase those, to be honest with you. And I'm going to go from bottom to top. With the range, I always would go this way, from bottom to top. So the first y value you see here is at negative 2. So I'd write negative 2 down. And then the second y value would be at 0. And then the third y value would be at 1. And then the next one would be at 3. And then finally the last one would be at 4. So I think that would be the appropriate way to write them, not the way I originally wrote them, like that. All right, so that would be the domain and the range. And then if this is the function h, then we could use function notation here also. So for example, h of 3, when x is 3, y is 1. So, right, you use that point, 3, 1. So h of 3 is equal to 1. H of negative 1 is equal to 3. H of 7 is 0. And so on. Right, and so that would be how we'd write the function notation for that particular function. All right, so that's a graph where you've got these discrete points for the graph. And then you could also have a graph that's a continuous graph, that you actually have a curve for the graph. So let's see. We're going to start off with something pretty simple here, but we're going to look at somewhat more complicated ones as we go along. Let's say we have this graph right here that's just a line segment. That's our graph right there. That's the graph of f. Now, one thing I always ask, and we did ask this last time also, is how many points are on that graph? And the most common answer I get when I ask how many points are on that graph is 2. But that graph has an infinite number of points on it. There's 2 points that are plotted, but there's an infinite number of points on that graph. Because the point has no dimension to it at all. It has no width, no height, no length or anything. So there's an infinite number of points on that graph. The graph does pass the vertical line test. So it passes the vertical line test. So it is a function. Right? So the graph passes the vertical line test, so it is a function. And so I would want you to be able to write down the domain and the range for this function. So the domain is the set of x values that are being used on this graph. And now this is a little bit trickier than the last problem as far as the domain, because it's not just a discrete number of points. Now, if I look at the x value negative 3 right here, notice that negative 3, there is no point on that graph that has an x value of negative 3, right? If you go up or down, right, you don't get to the graph at all. There's no x value on that graph that's negative 3. So negative 3 is not in the domain. On the other hand, positive 1 right there is in the domain, because you have a point on the graph right there that has an x value of 1. And 3 is in the domain because you have a point right there that has an x value of 3. And negative 1 is in the domain, right? You have that x value. Also, notice that 1 point 8, which is maybe right about in there. 1.8 is in the domain, right? You don't have to have just an integer or a whole number there. You could have decimals, irrational numbers. All those numbers fit inside there. So what I want to point out is that the domain on this problem, the domain on this graph, is all in words now. It's not the way we're going to write this ultimately, but all x's between and including -1 and 3. Right? You have every x value between -1 and 3 is going to be in the domain here. The way I like to look at this is I envision kind of walking along the x-axis. So there's a person walking along the x-axis, and they're trying to figure out the domain. And what this person is doing is they're looking vertically above them and below them as they walk along, right? And they're moving from left to right always. And the question is, where do they see the graph as they're looking vertically, and where do they not see the graph, right? When they start seeing the graph at -1, and then it's every x value between -1 and 3, which I shade right here, including 3, is in the domain. So it's all of those x values right there. Now we use, in algebra, we use interval notation to actually write out an interval like that. And the interval notation for all the x's between and including -1 and 3 looks like this. You simply write down the endpoints of the interval, and then you enclose it in brackets, and you're putting it in brackets because you're including the -1 and the 3. Notice the -1 and the 3 are both in the domain, and so we include both of them. And you include, when you put brackets, you are saying you're including those endpoints like that. All right, and so there's our domain, is in interval notation, is all the x's between -1 and 3. So when I write this notation right here that I'm pointing to, I'm saying you're talking about all the x's between and including -1 and 3. All right, so now let's look at the range on this same graph. So the range, you know, if you're thinking about the domain as being this person that's walking along the x-axis and they're looking vertically, then with the range, we're talking about y values. And so a way you could look at this is that you've got this person that is climbing along the y-axis, and they're climbing from bottom to top like this. And what that person is doing to decide the range is they're looking left and right. And they start marking range values when they see the graph either to the left or to the right, or both. So this person, as they're moving up the y-axis, the first place they see the graph would be right here at 1. Right? They see the graph at 1. And then they continue, you know, if you look at any value above 1 like that, they continue to see the graph, right? Look at all those horizontal lines and how they intersect the graph until they get up here, up to the value 5, right? That's the last place they see the graph. And then as they get above 5, they don't see the graph anymore. So shading that on the y-axis, these would be the values where they see the graph, to the left or to the right. It's either left or right, it doesn't matter which way. And it could be both, like I said. So the range, in words here, the range would be all the y's between and including uh, 1 and 5. Right, all the y's between 1 and 5. And so in interval notation for the range, what you would do is you'd write 1 down and 5 down, and you would enclose those in brackets. And you're telling somebody that you're talking about all the values between 1 and 5 and including 1 and 5 also. And that would be the range on this, for this particular problem. And so the domain and range is more complicated. We're going to definitely look at more examples of that, okay? So we're bridging into the next thing we're talking about with functions here, finding domains and ranges from graphs. So we're definitely looking at more examples, okay? Now with function notation, which we didn't talk about in this problem, you know, if I look at f of 3, for example, right, here's the x value 3, and all you're doing is going up to the graph to see what the corresponding y value is. So you've got this 0.35, so f of 3 for this function would be 5. F of 1 for this function, you look at the x value 1, and you go up to the graph, and you get the y value 3. So f of 1 is equal to 3. F of negative 1, you go to the x value negative 1, and you go up to the graph, and the y value, the corresponding y value would be 1. So f of negative 1 would be 1. I definitely would want you to be able to read function notation off of a graph like that. Okay? All right, so a lot going on with this problem, and I know I've drawn a lot of stuff out, but what we're going to do now is look at some more examples of what we're talking about here, okay? So what we're going to do is we're going to start with a graph, and then we're going to try to identify the domain and the range of the graph, and then also look at some function notation about that graph also. All right, so our next graph, and let's see, I'm going to put this in a different color here. So let's say our graph looks like this, a slightly more complicated graph. Say the graph looks like this. It's that line segment, but it's not finished yet. And then that line segment together like that. And so there's our graph right there. That graph passes the vertical line test, and so that's definitely a function. And so what we want to do is write down the domain and the range. So we'll call this function f. Let's just look at some function values, first of all, before we do anything else. So in our problem, f of negative 3, in this graph, f of negative 3, we go to the x value, negative 3, and we see the y value at that point right there, which is negative 2. So f of negative 3 would be negative 2. F of 1, we go to the x value 1, and we go up to the graph. In this case, we use that point, which has an x value of 1, and the y value is 2. So f of 1 is equal to 2. F of 4, we go to the x value 4. On the x-axis there, we would go down to get to the graph, and that would be at the point 4, negative 1. And so f of 4 is equal to negative 1, like that. And, you know, you could do something like f of 0. When f of 0, that's the x value 0, so you're actually starting at the origin, and you go up to the graph, and you get this point right here, which would be at 0, 1. So f of 0 is equal to 1. F of 3, the x value is 3, which is right there on our graph, and the y value for that point is at 0. So you get f of 3 to be 0. All right, so that's how you would read function notation from a graph. Definitely something I would want you to be able to do. All right, so now we're going to take the exact same graph, and let's go ahead and look at the domain and the range for that graph. So let's see, I'm putting the graph down again. So here's our graph. And we want to look at the domain and the range. And remember, the name of this function is f. So once again, we are talking about the domain. We're walking along the x-axis. We're going from left to right. And the question is where, as we walk along the x-axis, we'll mark a value on the x-axis if it's in the domain. We won't mark if it's not in the domain. It's in the domain when we see the graph vertically. Right? So we're always looking straight up, straight down. And we start seeing the graph here at negative 3, right? We see it down like that. And then we continue to see the graph. So I mark -3, and we continue to see the graph for all of these values, all of these x values, until you, remember, you're looking vertically up and down, until you get all the way over here to 4. At 4, we still see the graph right there. But then after 4, we don't see the graph anymore. And so the domain for our function f is all x's. I'm going to write this in words just for a problem or two, and then we'll stop doing that. Well, all x's between and including -3 and 4. And so we say that the domain for the function f in interval notation would be bracket 3 to 4, close the brackets. Right? Remember, the bracket means that that endpoint on that interval is actually part of the domain. All right, so now the range. So now with the range, remember what we're doing is we are climbing up the y-axis, and we're always going from bottom to top. And we mark a value on the y-axis if we see the graph either left or right. And we'll say that that value is in the range if we see it to the left or to the right. So the first place we see this graph is here at -2. Right at -2, we see the graph off to the left. And notice now some of the points, like right here at -1, notice we see the graph twice. That just means that we have a repeated y value. That's not a problem when you have a function. So that will happen. So as you move up the y-axis, where's the last place? What's the last y value where you see the graph? And that would be right here at 2, right? And so we start seeing the graph at -2. We mark all the y values between -2 and 2. And then we don't see the graph after 2. And so the range for this function would be all y's between and including -2 and 2. Okay, and so the range for this graph would be bracket -2 to 2, like that. And close the brackets. All right, and so we've talked about function notation with this graph, and we've also looked at writing down the domain and the range. Okay, so those are two things I definitely would want you to be able to do from a graph. And again, I tell you, if you can do that in college algebra, when you walk into a college algebra class, that will be awesome to be able to do that. All right, so next graph. So now we're going to move on to another graph. And we're going to gradually introduce new situations and how that relates to the domain and the range as we go through this kind of problem. So let's say that this is our graph. Let's see. I'm going to put this in a different color here. Okay. So our graph looks like this. Now this one is kind of different because it has an open circle somewhere. And here's our graph. Right, now the open circle at the end of that, one end of that graph means that that point is actually not in the domain for the graph, right? And so now this graph is a function, right? We'll call this g, so it is a function. We can write down function notation. So for example, in this picture, g of 3 would be equal to 1 because when x is 3, y is 1. G of 0 would be equal to 3. But notice that g of -2, here's -2 right here, and -2 is where that open circle is, right? So g of -2 is not in the domain. -2 is not in the domain because of that open circle right there, right? So g of -2 has no value. All right, so the domain and the range for this particular problem, for this function. So the domain, we're walking along the x-axis, always from left to right. Now, notice that as we hit -2, we still don't see the graph at -2 because of that open circle right there. So there's an open circle on the x-axis here if we're marking points on the x-axis. But notice any point past -2 right in here, you do see the graph. And so we start shading now, and we see the graph until we get to 3. And at 3, we do see the graph because of that closed-in dot. So that's a filled-in circle right there. And so the domain on G, the domain on G would be everything from -2 to 3, in between -2 and 3, but not including -2. And so the way you show that -2 is not included is you use a parenthesis on the -2, not a bracket. And then the 3 is part of the domain, and so that's a bracket right there. And so that would be the interval notation for the domain. So the parenthesis means there's an open circle, right? When you see an open circle, at a graph, you're going to have a parenthesis. When you see a filled-in dot, then you're going to have a bracket like that, right? And so, that's going to be frequent that you're going to encounter that. All right, now let's look at the range. So the range, we're climbing up the y-axis here. So there we are climbing up the y-axis. We're looking left and right, remember. In the first place, well, we don't see the graph at -1. At -1, not in the range because of that open circle. And so there's an open circle there at -1. And then we see the graph for all of these y values until we get to 3. And we do see it at 3 also because of that filled-in dot right there at 3. And so the range for G at -1, -1's not part of the range, so we put a parenthesis there. We have to include -1 because anything above -1 is part of the range. And then you go from -1 to 3 like that. And there would be our range for this particular problem. All right, and for those of you who are listening or watching live here, please stop me if you have a question here. I'm definitely going to give you some graphs and ask you to write down the domain and the range for those graphs. Now in college algebra, you look at more complicated graphs than what we're going to look at. Okay, so now we're going to do a few more examples here, but college algebra, you're going to look at it. It can get to be really tricky even if you have a graph to write down the domain and the range. All right, so the next problem, next graph. The next graph looks like this one. It has an open circle here, an open circle here. And this graph is actually part of what we call a parabola. And the graph looks like that one right there. Right? And so that graph is a function. It passes the vertical line test. So f is a function. Let's see. If I looked at some function notation here, f of 1 would be equal to 2. Right? Because here's 1. And the x value would be 2. And -1, notice the x value there is 2. So f of -1 is equal to 2 also. Notice that f of 2 is not in the domain because of that open circle. And f of -2, same thing. -2 is not in the domain because of that open circle. All right, so the domain for this function, we're walking along the x-axis from left to right. We're looking vertically. And we don't start seeing the graph at -2, but when we move past -2, we see it. So we start at -2, we put an open circle there at -2, and it's every x value until you get to positive 2. 2 is not in the domain either, and so we put an open circle there. And so the domain for f for this graph would be from -2 to 2. Right? Every x value between -2 and 2 is in the domain. -2 and 2 themselves are not part of the domain, and so those would be parentheses like that. And so that would be our domain. All right, the range. Now we're moving up the y-axis, right? We're looking left and right as we move up the y-axis. And at -1, we don't see the graph because of both open circles there, right? You look at a horizontal line right in there, and you don't see the graph there at -1. So there's an open circle there at -1. But then we start seeing the graph after we pass -1, and we see it until we get to y equals 3. That's a filled-in dot, and then we don't see the graph after that. So the range on f would start here at -1, but -1 is not in the domain or in the range itself, so we put a parenthesis there. And then we go all the way to 3, and then we put a bracket around the 3, because 3 is part of the range here. Okay, let's see. Now, we've talked about lines a lot. We've talked about linear functions. Let's look at a line. Right, we were talking about linear equations at the beginning of this chapter in this unit on graphing. We did a lot with that. So let's say we have this graph right here. All right, that graph definitely passes the vertical line test. So g would be a function. And now notice this graph has arrows on both ends. So when we're talking about the domain for this graph, notice that, well, it doesn't matter where I'm standing, right? If I'm standing on the x-axis, I'm always going to see the graph somewhere, right? No matter how far I go, remember those arrows mean the graph continues on forever in both directions. And so even as somebody standing way over here on the x-axis, right, that person's going to see the graph eventually up here, right? The graph's going to go through a point up here because of that arrow right there. And so the domain here, every real number is in the domain. And so the domain for g in words is all reals. And the way you write that in interval notation is it's always on the x-axis. It's always -infinity off to the left and +infinity off to the right. And so it's -infinity to infinity, like that. That's how you write all reals. Now, on a test, if you actually wrote the words all reals, I'd probably be okay with that. But on the test, I'm going to say use interval notation. So I'd rather you wrote it -infinity to infinity. And then the range on g, I've been using a different color for the range, so let's do that. So the range on g, notice that it's the same issue. This person climbing up the y-axis always sees the graph, no matter where they are. Because of those arrows, the graph continues on forever. And so this is also all reals right here. And so that's -infinity to infinity there as well. Definitely, so all slant lines, notice, a slanted line, the domain and the range are always going to be all reals. That will always be the case for a slant line. All right, and I don't see anybody stopping me. Nobody's got a question, I guess, and so we're going to go to another graph. Okay, so next graph, let's look at this is a parabola right here, but not just a part of a parabola like we saw a few minutes ago. This is the complete parabola here. So the graph would look like this, and there would be arrows at the ends on both ends like that. So those arrows mean that this graph continues to go down forever and also continues to spread out forever. both things, right? And so notice that the domain for this function, first of all, if we call this function f, let's just look at a little bit of function notation here. Make sure that you're okay with that. So f of 1, you could read f of, here's 1 right here, and f of 1 would be down here at negative 2, right? So f of 1 is negative 2. F of 4, let's see, here's 4 right here on my x-axis, and so it'd be the point 4, 1 right here. F of 4 is equal to 1. F of 5, here's 5 right here, and so you have 5, negative 2. So f of 5 is negative 2. Definitely would want you to be able to read function notation from a graph like that. And then the domain and the range. So notice that this person walking along the x-axis from left to right, because of those arrows, this person always sees the graph. So this person, where I've got them drawn right now, they will see the graph, even though that might be way the heck down here somewhere. The parabola is going to go through that point. So it's actually probably lower than what I've got right there. And so the domain for this particular graph, the domain for f is going to be all reals. It's going to be negative infinity to infinity, because the graph just continues to spread out forever in the left, to the left and to the right. Now the range is not going to be infinity to negative infinity to infinity. The range on f, this person who's climbing the y-axis does see the graph infinitely far. If you go down in the negative direction, that person will always see the graph because of those arrows. So where I've got this person right now, they can see the graph twice actually, right there, left and to the right. And this person right here continues to see the graph and continues to see the graph. But at 2, notice they stop seeing the graph after 2. And you always go from bottom to top. So the range is going to be from negative infinity to 2 with a bracket around the 2. Right? By the way, and I didn't mention this before, always parentheses around an infinity or a negative infinity. You never, ever, ever use a bracket around an infinity symbol. An infinity symbol is not a number. It's just something that's happening. So a bracket implies that you're stopping somewhere, which you're not doing here. So, all right, so the range would be parenthesis negative infinity to 2. The negative infinity symbol always goes on the left. Positive infinity symbol always goes on the right for both the domain and the range, like that. All right, so we've got function notation, domains and ranges from graphs. So we have a couple things left to do today. So we're doing good on time. Let's continue with function notation a little bit, but now with equations. Right, so we've moved on. We're getting away from graphs now. So now we want to look at equations and dealing with equations here and sketching graphs and function notation and things. So let's start off with a function like this, 2x minus 5, something relatively simple. So now, by the way, we're not going to be finding domains and ranges from equations like this. As you move a little bit further, that gets to be a harder question. That is a college algebra question. And so we're not going to be finding domains and ranges. But we will be looking at function notation. So f of 4. Here, I just picked 4 out of thin air. Right, that's when x is 4 here. And to find f of 4, if you're given an equation, right, you just substitute 4 in place of x. And you get 8 minus 5, which is 3. So f of 4 is equal to 3. Right, and that gives you the ordered pair of 4, 3, by the way. F of negative 8, every place you see an x, you substitute negative 8. So you have 2 times negative 8 minus 5, that would be negative 21. And so f of negative 8 would be negative 21. And the ordered pair we're talking about is negative 8, negative 21. All right, and we talked about function notation like that last time. So I think we're okay with that kind of problem. But now we're going to extend this. So what about f of t? Well, f of t at first might throw you a little bit, but don't do anything different with f of t. Every place you see an x, you're just going to substitute t. So this would be 2 times, in parentheses, t minus 5. Now, the only difference here is that I can't really do anything with that, right? That's just 2t minus 5. And so what do we have here? That f of t is equal to 2t minus 5. You don't usually see that written out as an ordered pair, but you absolutely could do that and put t as the x value and 2t minus 5 as the y value. That would be okay to do. You don't usually see it written that way, but you could. F of a plus b. Don't do anything different than what I did on the previous 3 problems there, the previous 3 function notations. Every place you see an x, you simply substitute a plus b. So this is going to be 2 times a plus b minus 5, right? The function was 2x minus 5, so in place of x, I put a plus b. And then, you try to do some arithmetic here, so that's 2a plus 2b minus 5, but there's not really anything you can do with that. And so you just leave it like that. So f of a plus b would be 2a plus 2b minus 5. Nothing else really you could do with that. All right, let's see. Let's look at g of x equals x squared minus 2x minus 3. So a different function here. So g of 8, every place you see an x, you'd substitute 8. So this would be 8 squared minus 2 times 8 minus 3. And so now a little bit of arithmetic to do here. So you have 64 minus 16 minus 3, and that would be 45. 64 minus 16 is 48, minus 3 would be 45. So you have g of 8 is 45 here. G of negative 10, you just need to be careful with the signs on a calculation like this one. Notice I always use parentheses, whether it's the x value is positive or negative, doesn't matter. I always use parentheses when I'm substituting like this. Every place I see an x, I put a set of parentheses. So you have negative 10 squared minus 2 times negative 10 minus 3. That's g of negative 10. So that's 100 plus 20 minus 3, or 117. And so g of negative 10 would be 117. Now, function like this, you could certainly use, look at other problems with function notation. So g of x, same function, 2x squared, x squared minus 2x minus 3. Is it? Yeah, minus 3. And so we could look at g of b, right? G of b, every place you see an x, you'd substitute b. I use parentheses. I'm going to just get in the habit of putting parentheses every place I see an x. So you get that expression right there, which you'd typically just write as b squared minus 2b minus 3, like that. And that would be g of b. G of a plus b. Every place you see an x, you substitute a plus b. Don't do anything different. And this is, in particular, this kind of problem is why I use parentheses when I'm substituting in function notation. So this would be a plus b squared minus 2 times a plus b minus 3. Now, a plus b squared, if you're going to do the arithmetic here, remember that's a plus b times a plus b. And we have talked about the square of a binomial a lot earlier in the semester. So remember, that's a squared plus 2ab plus b squared. And you could, if you go through the FOIL method with a plus b times a plus b, you can see where that comes from if you've forgotten. And then minus 2a minus 2b, using the distributive property there, minus 3. Now you get this really long expression here, and notice absolutely nothing you can do to simplify that, right? There's no like terms in there, so you're stuck with it like that. And that definitely could happen. These kinds of problems, by the way, you'll see in college algebra. And if you end up, like if you're a business major and you go on to take business calculus, then you will have to be able to evaluate this type of function notation in several different contexts in that class. So this will come up again in classes that use algebra after this one. All right. So a little bit more about function notation that I wanted to talk about before we finished class today. And so finally, I want to finish class here by looking at sketching graphs of functions. Now, the first thing I would want you to be able to do is, with some simple functions, is finding x and y intercepts. That will come up some on WebAssign on this section. So if you're given a function, I'd like you to be able to find the x and y intercepts. Now, I'm only looking at very simple functions here, by the way. This can get to be, believe it or not, can get to be very complicated, especially for finding x-intercepts for different kinds of functions. And I'm not definitely only going to look at some simple examples here. In college algebra, you're going to look at more complicated examples. So let's say I have a linear function like this, f of x equals 2x minus 5. Now don't forget how you find x and y intercepts. The x-intercept, you set y equals 0. And remember where y is, when you're using function notation, f of x is the same thing as y. So don't, you could even write it that way if you get nervous about it. Remember that f of x equals 2x minus 5 is the same thing as y equals 2x minus 5. So at the x-intercept, when you set y equal to 0, you get this equation. And then you just solve for x. You add 5, divide by 2, and you get x is 5 halves. And so the x-intercept's at 5 halves, 0. And then the y-intercept, you set x equals 0. And this is a linear function, and this is in slope-intercept form, so you should see the writing on the wall that you're going to get -5 for the y-intercept. And you didn't even need to do any calculations there. Since it was in slope-intercept form, you could have done that. And with a line, with the x and y intercepts, you've really got enough that you don't need to plot any more points. Since it's a linear function, right? This is a linear function right here. Since it's a linear function, you don't need many more points besides the intercepts, and you can sketch the graph. So 5 halves is 2.5, 0, -5. It's way down here. And there's your graph. Like that. It goes off the screen below there. All right, so I definitely want you to be able to find the intercepts here. And I would also, want you to be able to sketch the graph. Because it's a linear function, you don't need anything besides the intercepts. If it's not linear, then you are going to need some more points. So let me show you what I'm talking about here. So let's say I have f of x equals 4 minus x. Well, let's say x squared minus 4. Yeah, that's what I want to do. All right, so the intercepts there, the x-intercepts, what do? You set y equal to 0. And this is a little bit more involved here. You set y equal to 0, and you get 0 equals x squared minus 4, and you get a quadratic equation. Now that quadratic factors is x plus 2 times x minus 2. And so notice you end up with 2 solutions to that equation. You end up with -2 as a solution, and you end up with +2 as a solution. So this is a graph that actually has 2 x-intercepts at -2, 0, and at 2, 0. All right, and then the y-intercept There's no slope-intercept form here or anything, but the y-intercept is not hard. You set x equals 0, and you get y equals 0 squared minus 4, so you just get y equals negative 4. So you have 0, negative 4 as the y-intercept. All right, now you might plot some points here in order to get the sketch of the graph. So this is a place where you might make a table of values. We were doing this back with lines, some, but it's more important now with graphs that are not lines. So if we make a table of values here, we've already done some of these if you think about it. So let's see. If we do negative 3, negative 2, negative 1, 0, 1, 2, and 3, some of these are already done. Right, negative 2 we know is 0, and positive 2 we know is 0 from the intercepts. And 0, negative 4, we know that one right there. So when x is negative 3, you have f of negative 3. Be careful, that's negative 3 squared minus 4, which is positive 9 minus 4, or 5. Negative 1, you get negative 1 squared minus 4. So that's 1 minus 4, negative 3. Notice the f of 1, you get positive 1 squared minus 4, and that's still negative 3. And then f of 3, right here, you get positive 3 squared minus 4, and that's positive 5. And so this graph, let's see, let me make sure I get enough space here to get the points that I want on here. So let's see, let's plot these points. So negative 3, 5, 1, 2, 3, 4 is up here. There's negative 3, 5. Negative 2, 0 is here. Negative 1, negative 3 is here. And 0, negative 4 is right here. That's our y-intercept. And then you've got 1, negative 3 is right here. 2, 0 is another x-intercept. And then you have 3, 5. And so notice this graph, when you plot these points, this graph ends up being a parabola. Looks like this. Now you're going to look at more with parabolas in college algebra certainly, but for right now what we need to be able to do is I want you to be able to take some parabolas and find their intercepts and be able to plot points to sketch the graph, not anything beyond that. All right, so now I'm not going to sketch the graph on this one, but let's say we just have f of x equals x squared minus 4x minus 21. If I ask you to find the x and y intercepts here, I'm not going to have you graph this, but if I want you to find the x-intercepts, let's see what we can do here. So we set y equal to 0. So you get 0 equals x squared minus 4x minus 21. And notice that is a quadratic also, and it's factorable. So you have x minus 7 times x plus 3. Set each factor equal to 0. And you end up with x equals 7 and x equals negative 3. And so our x-intercepts, there's actually two x-intercepts. One's at 7, 0, and the other one's at negative 3, 0. Parabolas frequently have two x-intercepts. The y-intercept, much easier. Find the y-intercept here. We set x equals 0 in the equation. And notice here when you set x equals 0, you get y equals 0 squared minus 4 times 0 minus 21. Everything goes to 0 except that 21. You get y equals negative 21. And so there's our y-intercept at 0, negative 21, like that. So a graph or in a function like that, I'd want you to be able to find the intercepts. Maybe not necessarily to graph it by plotting points, because there are some issues with plotting points to sketch a graph like this. But at the very least, to find the x and the y intercepts. All right, finally, let's see. I have one more example to work here. Let's graph. Don't worry about intercepts here, but let's graph by plotting points. G of x is equal to the absolute value of x minus 3 minus 1. The absolute value of x minus 3 minus 1. So here, what I would want you to be able to do is simply graph this by plotting points. So make a table of values and be able to plot points here and sketch the graph. All right, so I'm going to start at -2, and then -1, 0, 1, and 2. Now I'm going to leave some room here at the bottom. We may decide we want more points than this, so we'll see. So when x is -2, we have g of -2 is the absolute value of -2 minus 3 minus 1. Now the absolute value of -2 minus 3, that's the absolute value of -5 minus 1. And the absolute value of -5, don't forget, is positive 5, right? Absolute value is always positive. So you have 5 minus 1 or 4. And so you have -2, 4. After you've done one of those, they get easier as you see how this is going to work out. So when x is -1, you have -1 minus 3. Okay, so that's -4, but the absolute value of -4 is 4. So you have 4 minus 1 or 3. So g of 0, you have the absolute value of 0 minus 3 minus 1. So that's the absolute value of -3, which is 3. Or 2. G of 1, you have absolute value of 1 minus 3 is the minus 1. So the absolute value of -2 is 2 minus 1, which is 1. And this just looks like a line so far, right? G of 2, you get the absolute value of 2 minus 3 minus 1. So that's the absolute value of -1, which is 1 minus 1, or 0. If you do 3, do another point. See, so far, by the way, just let me show you what the points look like right here. And you might say, well, I don't need any more points. I've got this graph with no problem. I know what this looks like. It looks like a line. And you would certainly be justified in thinking that with just these points. There's -2, 4, -1, 3, 0, 2, 1, 1, 2, 0, and then g of 3, which is the next one right here. You have the absolute value of 3 minus 3 minus 1. 3 minus 3 is 0, so that's 0 minus 1, which is -1. All right, so far, nothing's changed here. Right, you get -1 right there. But look what happens at 4. G of 4 is the absolute value of 4 minus 3 minus 1. 4 minus 3 is 1 minus 1. Absolute value of 1 is 1. And you get 0, and look what happens right there. First of all, this is 0. And when you plot that point, you get 4, 0. The graph is now turned. It's no longer a line. Right? It's clearly not going to be a line. You try another point there. You go on to 5, and you're going to get that 5 is equal to 1. And so g of 5 is 1. And so you get a graph that actually looks like this. It looks kind of, you might have thought it was a line at first, but it's kind of a V-shaped graph like this. Right? And that's typical for absolute values like that. So I'd certainly want you to be able to plot points to sketch graphs like this. Okay. All right, so that finishes what we want to talk about today. We are going through the material. Remember, this is the material out of section 3.5 and 3.6 of the intermediate algebra book. That's what we've been covering from the intermediate algebra book, and that I have put that material in the section on syllabi and other documents. So in syllabi and other documents, at the bottom of your Google site, you'll see the file with sections 3.5 and 3.6. So you can go to that material definitely, and you can definitely work problems out of the textbook out of that section. It doesn't affect how you're doing WebAssign at all. The WebAssign just carries on. But if you're looking for textbook material, that's where it's located. All right. All right. So I hope you have a good weekend. Does anybody who's with me live right now have any questions?
Questions so far?
All right. Everybody's quiet. Taylor says no. Sandra says no. Gian and Raina, we're going to say you say no also, I guess.
Yes. No questions.